It's time to start next session. Next speaker is Dr. Martina Lippi. She's an assistant professor with the engineering department at Rome Tre University, Italy. So if you are ready, please start.
Yeah, thank you for the introduction and thank you for inviting me. So today I'll be talking about two concepts in human multi-robot teams that are human safety and task allocation. So first of all, let me a bit recap what I mean by human multi-robot teams. So here I mostly consider multi-manipulator teams that can interact with multiple humans. So the objective is to enable human and multi-robot systems to work with each other in order to accomplish desired tasks. And the main advantage is that in this way, we can combine the high human reasoning skills with the very high robot's physical skills. I'm trying to change the slide. Okay. But then, of course, there are some challenges that we need to address. So the presence of the human in the loop requires to dynamically adapt the robot's behavior. That means that every time there is a change in the human behavior, we need to understand what each agent has to do. So the robot have to understand what they have to do in order to adapt to the human change. And also we need to be compliant with any constraints of the multi-robot system. So for example, if we think about a cooperative transportation task, then of course we can't have like independent adaptation strategies of the robots, but they have to be properly coordinated. And this of course becomes even more challenging in a distributed setting. So today I'll be focusing on just two of the very many enabling technologies for the human multi-robot interaction that are the human safety in workspace sharing scenarios and the human multi-robot task allocation. So in the first scenario here on the left, we assume that there are multiple robots whose collaboration could be tight, like here, or could be loose. And then, of course, we have one or multiple humans. And the objective is to always ensure the human safety. That's like the basic requirement that we always need to ensure when we share the same workspace. But then in this setup, we assume that each agent knows the task to accomplish. Well, then we wonder how we can actually assign these tasks. So these agents are, of course, really different. So they have really different features and different tasks could be needed to be associated with these agents. So for example, the human could be more suitable to carry out some like more reasoning tasks, while the robots could be more suitable for some physical tasks. And so we'll be interested in understanding what could be a way to allocate these tasks. And then, of course, we could combine these two aspects and define a safety-centered human multi-robot task allocation. And that's where we'll go. So let's start with the first aspect, that is the one of the human safety for workspace sharing. So here, the objective is to, as I said, ensure the human safety. So what we could do is that we could assess the human safety through a safety index, which takes into account the positions and velocities of all the points of the structures of the manipulators. And then we can try to have a safety condition that basically states that the safety index must be greater than or equal to a minimum value. So to try to formalize this a bit, we can consider that we have a cooperative desired trajectory. So this desired trajectory takes into account all the robots of the team. So that could be, for example, representative of the formation of the team and the centroid of the team. And then we want to properly modify this desired trajectory in order to ensure the safety condition. So in order to ensure that the safety index is always greater than or equal to a minimum value. And this minimum value could be, for example, selected in order to ensure a minimum safety distance or to account for some psychological aspects. And then, of course, we want to track the resulting trajectory, and we want to do that in a distributed way in order to have scalability of the system. So in this regard, our contributions were to provide some safety guarantees, so to actually provide that we are able to enforce this safety condition, and also to develop a solution which is suitable for multi-robot scenarios and works in a distributed setting. So this is just like a high-level overview of the solution. So we have a two-layer architecture, where in the first layer, the objective is just to understand how we need to modify this cooperative trajectory in order to ensure the human safety. And then at a lower level, we can actually track this decided trajectory in a distributed fashion. So here in this low-level controller, we resorted to several distributed observers in order to define the local control law that allows to track the reference trajectory. And going back to how we can define the reference trajectory, basically we can track the nominal one as long as the safety index is fine, so as long as it's greater than the minimum value. And then we can start scaling the trajectory when we reach the minimum value. That means that basically we only try to modulate the velocity of the team, of the robots team, without modifying the path. And this is generally desirable in industrial settings. But then, of course, if this modulation of the velocity is not enough to guarantee the human safety, that we also can activate an emergency procedure that relaxes these constraints of preserving the path. So here I will not go into the details of these, how the trajectory scaling is done, but just briefly, we can parameterize the nominal trajectory with respect to a scaling parameter, and then we can define bounds on this scaling parameter in order to ensure the human safety. And by properly considering these bounds, we can finally derive the following scaling parameters update law, which ensures that we actually fulfill the safety condition. So here we have an example of how this approach could work. So here we have two robots which are cooperatively transporting a box, and the trajectory is modified according to the human hand motion. So we can see that the trajectory was slowed down in order to guarantee the human safety, and the safety index is saturated. But then here, since it's the modulation of the velocity only is not enough to guarantee the safety, we activate an emergency procedure that relaxes this constraint of preserving the path. And once the safety index is fine again, we can recover the desired trajectory. So far, I just considered the constraints in terms of tasks of the robots. So, for example, that we need to take into account the cooperative task that might be expressed in terms of centroid or formation. But then, of course, there are some other constraints when we deal with multiple robots. And in particular, we have kinematics and dynamics constraints that we can integrate in this system by resorting to control barrier functions formulation. So here the idea is that with this CBF formulation, we can ensure the human safety and properly scale the trajectory while also ensuring kinematics and dynamics constraints. Okay, so once we solve this human safety aspect, we can focus on the human multi-robot task allocation. So here, the scenario is the following. So we have a set of tasks to perform, and we have a set of agents, which could be robotic agents and human agents. And the first thing we need to do is to define the offline optimal task assignment. And in doing that, we consider the nominal parameters of the tasks and the features of the agents. So first of all, we need to define what agent does what and when it has to start and when it has to finish. But then, of course, we have humans in the loop, so everything can change once we deploy the system. And that means that the task parameters will be time varying, and also the human preferences will be time varying. And this implies that we need, of course, to update online this task assignment. And this must be like, this must take into account these time varying parameters and human preferences. So just to, here we just try to formalize a bit what we try to do. So here we have a set of agents, we have a set of tasks, and we want to understand how to allocate these tasks to the agents in such a way that the overall quality of the tasks and the workload and the make span, which includes also the switching cost, are optimized. Then, of course, we want to fulfill all the task constraints, like, for example, we can have precedence constraints or spatial constraints or minimum level of accuracy constraints, and all of them must be fulfilled. And then we want to take into account the human preferences. So, of course, every time we have a human, we should try to accommodate his or her preferences. And finally, we also want to take into account the fact that some tasks could be carried out in a collaborative fashion. So, for example, if we have to carry a very heavy load, one robot could not be enough. So we could go for a robot-robot collaboration or a human-robot or human-human collaboration. And then, of course, we want this framework to be adaptable to changing agent parameters. So in this regard, the contributions that we made are that we introduced the concept of human supervision in an optimization formulation. We'll see it in a bit. And also we formalized this concept of collaborative tasks and human preferences on an optimization problem. And then, of course, we defined the closed loop rescheduling framework, which allows to adapt to these dynamic agents. And here we have an overview of the proposed approach. So first of all, we have the agents, we have the tasks. So we can define the constraints of our system. And based on these constraints, we can solve an optimization problem, which is formalized as a mixed integer linear programming problem, which allows to define the assignment of the tasks to the agent. Then, of course, we know all the tasks that the robots must perform. We know when they have to start and when they have to end, and we can do some trajectory planning, and we can execute these trajectories. But then at runtime, of course, we need always to update the parameters of the tasks and also the human preferences. And this implies that we may also need to update the constraints. And if we have new constraints and if we have new parameters, then of course we have to check if we need to do a reallocation of the tasks. So at this point, we need to understand actually how to realize this mixed integer linear programming problem and how to realize the reallocation. So regarding the optimization problem, this could be a way to go. I'll not go into the details of these equations. I just want to highlight the peculiarities that we have when we consider a human multi-robot team. So in particular, we introduced this option of the human supervising the robots. So the idea is that, of course, the human has this high reasoning skill. So the human could help the robot every time it's necessary. So if, for example, the robot is not confident enough to be able to carry out the task, then the human, of course, could help. And this is formalized by having some proper allocation variables, which are these supervision variables. And then, of course, and these are exploited in a bunch of constraints. And then, of course, we also have constraints related to the human preferences. And here we also have the introduction of these possibly collaborative tasks. So once we have the allocation, we need to understand when the reallocation is necessary. And we run reallocation every time the constraints or human preferences or on remaining tasks are not met. So if, for example, the human takes more time than expected to carry out a certain task, then if he has to perform the same task in the future, then we may need to reallocate. And then we also reallocate when there is a drop in the optimality performance. And in doing so, we actually consider this approximation to understand if there is an optimality performance drop. So we consider the nominal cost on the remaining tasks and the updated cost on the remaining tasks. And we check if this normalized difference is greater to a certain threshold. And then, of course, the system is dynamic, so new batches of tasks could arrive, and we need to reallocate if this happens, and also if there is any change in the available resources. And we tested this approach in a box filling task. In particular, here we are filling these boxes with grapes. And this is inspired by a European project, Canopies, which exactly focuses on this human multi-robot paradigm for agricultural settings. And that's why we have this agriculturally inspired case study. And here we can see the one experiment. So first of all, we have the allocation in the bottom left, and the human performs the first task, that is to put this paper cloth. Then he actually asks for skipping the next task. So he expresses a preference and the reallocation is made. So here we see actually a new plan with respect to the initial one. And here the human helped the robot to properly position one of the grapes. So the human was assigned to a supervision task. And this happens for a bunch of grapes. So every time it's a grape must be placed in the corner, we actually also assign some supervision in order to be sure that it's properly placed. But then here we are at the safety center, the human multi-robot task allocation. So in this human multi-robot task allocation that we just saw, of course, we have some safety features. I didn't highlight them, but they are like loose safety features. So we want to understand if we can actually have a safety-centered task allocation. And the way we are doing that is that we consider 3 safety levels at planning time. So we consider that the human robot tasks cannot be simultaneously executed. So if they are too close, of course, this is an unsafe state. Then we consider that the human robot tasks could be also executed simultaneously with limited velocity. And this is a monitored condition. And then we consider the case where the human robot tasks can be executed simultaneously with full velocity, so that the working condition is completely safe. And this is just done offline when we want to understand what's the reallocation. But then, of course, online, we need to be sure that everything is going fine. And then we integrate the trajectory scaling we saw at the beginning in order to guarantee the human safety if that's needed. And here we have just some preliminary results. This is actually something we are working on now. And here the task is this, again, this box filling task where we have some bottles, and we also have to place the caps on the bottles. So actually there was a supervision task, and the human helped the robot to release the bottle in the proper position. And here I just want to point out that like now, the human is very close to the robot on the left, and that implies that the robot actually chooses the monitor the condition to work, so that reduces its velocity, its operating velocity. And then at the end, like they keep working on the allocation, and at the end they could fill all the boxes. Okay, so in conclusion, in this talk, we talked about 2 important issues in human multi-robot teams, which are, of course, the human safety and the human multi-robot task allocation. But of course, there is still a long way to go. So some aspects we are working on now and we are planning to work on in the future are that we need to have human awareness when there are some unplanned tasks. So the human could choose just to do something completely different and something completely off the plan. So we need to be aware of that. And then also to include some prediction in order to have proactive behaviors. And then another issue is actually how to evaluate that the human is satisfied with the plan. So we define this cost function, but then there are also some qualitative metrics that we need to take into account. And finally, one issue in human-robot interaction in general is that, of course, the solution must be super efficient, since the deployment must be fluent for the human. And then we need to work on more efficient solutions to actually carry out the allocation. So with that, I conclude my talk, and thanks a lot for the attention.
Are there any questions?
So thank you for insightful talk, and I'm very interested in your idea of that, how to say, the learning, the human preferences in online, and also in the conclusion, you have a many to-do list in what kind of human aspect we need to learn or estimate. So, but I think to learn such kind of preferences in online is very challenging, right? So what kind of, for example, how frequently you want to update, or what kind of estimation system you considering now? Could you tell me a broad idea of that?
Yeah, actually, yes, that's like an entire world of research. So to understand the human preference is like a very tough task. Now we are considering explicit communication. So we are considering that the human actually talks with the robot and can say, okay, I don't want to do that, or I want to do that. But there must be also implicit ways of communicating could happen, of course. And like this is something for sure that it must be integrated in such a framework. And this is something like we really want to look into, but it's like not present now in the framework.
Okay, so maybe if you can run the such kind of models, you can easily integrate your optimization problem, right?
Yeah.
Okay, so your framework is very you can embrace so many.
Yeah, that's actually kind of flexible. So if you're able to do that, then of course you can integrate this aspect as well in the optimization problem, and then use the same framework. I mean, the extended framework.
Okay, thank you for your answer. And are there any other questions from audience?
Thank you for the very nice talk. Other questions? You talked about resource allocation. Would the framework facilitate that you could add, like you have a task and then another human comes in, and then what would the framework do?
Yeah, that's like perfectly doable. So you could have like this situation could be easily handled with this setup. So you could just like update your resources, and then you run again your optimization problem, and you can find another optimal solution, which also takes into account like the presence of another human. So that's perfectly doable.
Okay, thanks.
Thank you.
Thank you very much. I really like the talk, and I have plenty of questions, but one question I would like to ask, since I also do like optimization for task allocation and humans and so on. And the question I like to ask is about feasibility. Say it's not feasible for some reason, the human, we don't have a precise model, and for some reason we have problem solving this problem, so we can relax it some way to get feasibility. But that means that we don't get the optimality that we wanted at the beginning. So what's the point of optimization in all this?
Yeah.
And what is the alternative?
Yeah, actually, I mean, that's a good question. So of course, when we have humans, like it's tough to say that something is optimal, because you can't really say what's the best for the human. There are some like very subjective metrics that you should take into account. So the idea here is that we do our best by defining this cost function that is like it's reasonable. But then of course, like it could happen that it could also happen that the human is actually not happy with the solution, so that it's optimal for you with your optimization cost, but then it's not optimal for the human because there is something we are not able to model. So the answer is that we do our best, so we do what we consider that could be optimal. So, but of course, then there might be issues in actually considering what the human prefers. And also there could be issues in feasibility. So the idea is that you could do your best, then you try to be as close as possible to the optimal solution that you believe. But so actually also in the reallocation strategy, we don't go for the fully optimal solution. So we, because since we are using a MILP problem, we have NP hardness computational issues. And so we don't run every time the MILP, but we do have a kind of heuristics just to understand if the new, the plan with the new parameters is still okay or not. So we are not always fully optimal. Thank you.
Okay, so it's time to move next speaker. Thank you so much again.